Part 3, Hardy-Weinberg. Now, remember, p squared plus 2pq plus q squared equals 1. That's great to know, but why do we do this? Why do you want to know these things? The reason people wanted to know, I guess I could go back to some original questions like, gosh, how many heterozygotes are mixed into my homozygous dominants? How do I get a purebred line? Questions like that. But other reasons we do that is that we go in here, and I got my yellow highlighter out, is that if the proportions of dominant heterozygote and recessive homozygous do not match the Hardy-Weinberg proportions, then one or more of the 5 assumptions has been violated and is causing evolution. Let's go back to those 5 assumptions. These turn out to be really important assumptions. Because all these are the 5 ways, and you've seen the film, The 5 Fingers of Evolution, these are the ways that allele frequencies change. So if none of these things are happening, then allele frequencies are not changing, and these proportions will stay forever until something happens that changes the frequencies of alleles by removing one of these phenotypes disproportionately more often than others, or favoring one in some way. And so that's the big deal here. So we can identify if evolution is occurring if, given the frequencies of big A and little a, that our organisms are not in p squared 2pq plus q squared proportions. Now, there are 2 kinds of math problems that we get from this. The type 1 math problem is here. When we can assume, and we will always tell you in this class, will come out right front, you can assume Hardy-Weinberg equilibrium. And that is cool shorthand for Hardy-Weinberg equilibrium, by the way, HWE. And we use this information then to find P and Q, or the proportions of DH and R, whichever we're missing, given that information. And I'll show you how to do that in just a second. But we know already that if you know, for example, Q, you can find P, and because they add to 1. And then from there, you can make p squared 2pq plus q squared. It's a piece of cake. Now, let's go to type 2 problems, are a little trickier. In these, we cannot assume Hardy-Weinberg equilibrium, but we're usually given some other information. We have to count bodies, I like to say, to find P and Q. That means we have to count up the number of homozygous recessives to find Q squared, right? The number that's R. Or we have to actually grind up all the individuals and find out how many are big A's and how many are little A's. They usually give us a genetic test in these so that we know how many heterozygotes they are, because you can't really solve the problems if you don't know how many heterozygotes they are. And then we test to see if the number of DH and R, the dominants, heterozygotes, and recessives, are in Hardy-Weinberg equilibrium. If they're not in Hardy-Weinberg equilibrium, then evolution is happening. And we don't know for sure which of those 5 assumptions is being violated, maybe more than one, but something is causing the allele frequencies to change such that they don't match the proportions of DH and R. That's the dominant, heterozygote, and recessive genotypes. So, next step is to do some problems.